Section 12.5. Particles exhibit wave-like behavior. This is proposed by de Broglie. He also proposed a quantitative equation. Lambda is equal to h over p. H is the Planck constant. P is the momentum of the moving particle. Lambda is the wavelength of this particle. Let's look at a few examples. The wavelength of an electron moving at 2,000 kilometers per second is observable. Lambda is equal to h over mv. Therefore, we plug in the three numbers and we see this wavelength of the electron is 0.7 nanometers. It can be measured, it can be observed. The wavelength of a baseball moving at 50 meters per second is unobservable. Again, you plug in the three numbers. The wavelength of the baseball is 10 to the power of negative 35 meters. This short wavelength is unobservable. In summary, it's just easier to observe the wave-like properties of particles with a very small mass, such as electrons or atoms. And because electrons are much lighter than atoms, it's actually again easier to observe the wave-like properties of electrons than atoms. If we are looking at a particle that moves at a speed near the speed of light, we need to make some corrections to its mass. The moving mass is the rest mass divided by the square root of 1 over v squared over c squared. So you need to know the speed of the particle. Plug it in here. Usually this is negligible. Usually v squared over c squared is negligible. But if the speed of the particle is more than 10% of the speed of the light, and then you are looking at 0.01 here. All right. So again, this is a correction that needs to be made for particles that move at a speed near the speed of light. Now again, let's look at the statement. Particles exhibit wave-like behavior. And this is related to the Heisenberg uncertainty principle. The exact values of the position and momentum of particle cannot be known simultaneously. And why is that? Well, if you think of a wave with a certain wavelength, that means we will be able to have a certain momentum, right? A wave with a certain frequency has a certain wavelength. Using de Broglie's relation, wavelength is equal to h over p. That means p is certain. The momentum is certain. However, if you imagine a wave with a certain frequency, where is the position of the wave? Where is it? It's all over the space. A wave occupies the entire space. We do not know where the wave is exactly. On the other hand, if you have a particle with a certain position, that means it's not a wave with one fixed frequency. I'm going to show you some visual examples. Let's look at a wave. This is a cosine wave. And let's look at cosine 2x. Cosine x has a wavelength of 2 pi. Cosine 2x has a wavelength of just 1 pi. You can go from here to here. This is 1 pi. You can go from here to here. That's also 1 pi. And also you can go from here to here. That's also 1 pi. Right? It's also 1 pi. Now I'm going to combine cosine x and cosine 2x. So this green is cosine x. This dark blue is cosine, the red one is cosine 2x. And this dark blue is the average of cosine x and cosine 2x. All right, so if you look at this wave, you do not know its wavelength exactly. It can be pi, it can be 2 pi. This cosine x has a wavelength of 2 pi, cosine 2x has a wavelength of pi. Now let's combine 4 different waves, cosine x, 2x, 3x, and 4x. We get a combination here. What's the wavelength of this? I don't know. It's 2 pi, it's pi, it's 2 pi over 3, it's 2 pi over 4. 16 such waves, 64 such waves. This time I'm taking the average of 64 waves, cosine x all the way to cosine 64x. Now let's look at this combination. Do we know its wavelength? Well, we're not sure. It can be 2 pi, it can be pi, it can be 2 pi over 3, 2 pi over 4, all the way 2 pi over 64. We don't know. But now let's look at the position. We are now more certain about the position of this combination. It's actually around the 0 point. So this time we are less certain about the wavelength, but more certain about the position. So again, how do we calculate the momentum of this wave functions, the combinations of the wave functions? We'll use this equation. For cosine x, lambda is 2 pi. The momentum of cosine 2x is simply h over 2 pi. That's it. But what if we are looking at a combination of 2 waves? If we have cosine x and cosine 2x, we have 2 different wavelengths. We have 2 pi and pi. So the momentum of the combination of cosine x and cosine 2x, well, can be h over 2 pi. It can be also h over pi. What about a combination of 64 cosine functions? And then we will be able to have 64 different wavelengths and 64 different momentum. So again, if we look at this combination, it's called linear combination of 64 waves. It's impossible to determine the exact value of the wavelength of this combination. And it's impossible to determine the exact value of the momentum. Again, this is because this de Broglie relation, momentum is h over lambda. So this momentum now depends on this value n. So h over lambda is h over 2 pi over n. Therefore, it's nh over 2 pi. When you have a 64 wave combination, this n can be from 1 to 64. So you have 64 different values for the momentum. Now again, when we are looking at this combination, this is a formula. The shape is right here. When we are looking at this, it's impossible to determine the exact value of its wavelength because there are 64 different values. There are 64 different values for the momentum. However, in this case, when we are uncertain about its momentum, we are more certain about its position. And this is Heisenberg uncertainty principle. All right. If you are interested in this, feel free to include more waves. If you include more than 1,000 waves, you will see a straight vertical line. That means the combination of such 1,000 waves will be almost completely delocalized at point 0.